Hello everyone, my name is MALHAR VAGHASIYA. Today, I would like to present our discrete mathematics project, finding the shortest path in Google Maps using graph theory. Here are our team members. Introduction. Google Maps is a popular navigating tool used to find the shortest path between the start location and destination. To find this shortest path, a mathematical concept called graph theory is used. In this presentation, we will learn how Google Maps uses the graph theory to find the shortest path. Graph theory. Graph theory is a branch of mathematics that studies the relationships and properties of graph. A graph consists of a set of vertices connected by edges. Some of the key concepts of graph theory used in our application are node, edge, path, and weighted graph. Finding the shortest path. We can consider Google Maps as a big giant graph with nodes and edges to figure out the shortest path to travel. Dijkstra's algorithm is one of the many ways to find such path. Let us first see the algorithm and then an example to understand its application to find the shortest path. Here is Dijkstra's algorithm. Rules with Dijkstra's algorithm. From the starting node, visit the vertex with the smallest known distance. After having moved to the smallest distance vertex, check all the neighboring nodes. Compute the distance for the neighboring nodes by adding the distance of the edges from the initial vertex. If the distance we are checking is less than a known distance, update the shortest distance. Here is an example. In the following figure, A, B, C, D, E, F and G are the vertices. We need to find the shortest path from vertex A to vertex G. Step 1. We initialize a table. Let all the distance start from infinity. Step 2. We start visiting points from the starting point A. We keep track of the nodes we have visited and have not visited yet in two sets. The visited is an empty set and the not visited is a set of A, B, C, D, E, F, G. Step 3. Visit each node according to the rules we discussed before. Visit the point with the smallest node distance. Right now, every point has a distance of infinity except for A itself, so we will visit node A. Examine its neighboring nodes and calculate the distance of them from the node we are visiting. Distance from node B is 4 and distance from node C is 3. Check if the calculated distance is less than the currently known shortest distance. If it is less than the currently known one, then update the currently known distance to the shortest distance and add the previous to be A, since that was where we came from. Given is the updated table. Step 4. Repeat the steps. Visited is A and not visited is B, C, D, E, F, G. Next, look at the node with the smallest distance that has not been visited yet. In this case, node C has a distance of 3, which is the smallest distance of all the visited nodes. So node C becomes our current point. Repeat the same procedure as before. Check the unvisited neighbors of C and calculate their shortest path from our origin node A. The unvisited neighbors of node C are nodes B, D and F. Distance to B is 8, distance to D is 11, distance to F is 7. Compare with current values. Notice that the distance to D and F via node C, which are 11 and 7 respectively, are shorter than our currently known the shortest distance, which is infinity. We can update the shortest distance and the previous vertex in the table for D and F since we found a better path. This is the updated table. Visited is AC and not visited is B, D, E, F, G. The next current vertex is B since it has the smallest distance which hasn't been visited yet, which is 4. The unvisited neighbors of node B are nodes D and E. Distance to D is 8 and distance to E is 10. Compare with current values. The distance to D and E via node B, which is 8 and 10 respectively, are shorter than our currently known shortest distance, which is 11 and infinity. This is the updated table. Visited is ACB and not visited is DEFG. The next unvisited node with the shortest path is F. So F is our next current vertex and the distance is 7. The unvisited neighbors of node F is node G. Distance to G is 17. Compare it with the current value. The distance to G via node F, which is 17, is shorter than our currently known shortest distance, which is infinity. This is the updated table. Visited is A, B, C, F and not visited is D, E, G. Next, we chose D as our next current vertex since it has the shortest path among the unvisited nodes, which is 8. The unvisited neighbors of node D are nodes E and G. Distance to E is 10 and distance to G is 11. Compare with current value. As you can see, the distance to G via node D, which is 11, is shorter than our currently known shortest distance, which is 17. This is the updated table. Visited is A, B, C, D, F and not visited is E, G. E has the shortest path among the unvisited nodes, which is 10, so we choose E as our next current vertex. The unvisited neighbors of node E is node G. The distance to G is 13. Compare with current value. The distance to G via node E, which is 13, is not shorter than our currently known shortest distance, which is 11. So we won't update the table. This is our final table. So the shortest distance between vertex A and vertex G is 11 units. Hence, we have found the shortest path between the two vertices using Dijkstra's algorithm. Thank you.